Supersonic flight once seemed an insurmountable barrier, a realm of destructive forces that tore aircraft apart. Early aviators faced an invisible wall as their designs approached the speed of sound, encountering phenomena unknown to subsonic aerodynamics. The very air, typically a medium of support, transformed into a hostile environment, presenting challenges that demanded entirely new paradigms in engineering. Breaking the sound barrier, Mach 1, meant contending with radical changes in airflow. Below Mach 1, air flows smoothly over a wing. As an aircraft accelerates, local airflow over curved surfaces can reach Mach 1 even if the aircraft itself has not. This creates localized shock waves, leading to buffeting, loss of control, and a dramatic increase in drag, often termed the sound barrier due to its seemingly impenetrable nature. The critical aerodynamic demon at the heart of the sound barrier was the transonic drag rise. As an aircraft approached Mach 1, shock waves formed on its surfaces, separating the airflow and drastically increasing resistance. This phenomenon demanded immense power just to maintain speed, often exceeding the capabilities of early jet engines, making sustained supersonic flight practically impossible without significant design innovations. Engineers tackled drag rise with crucial design principles. Thin wings minimized the cross-sectional area exposed to airflow, reducing the strength of shock waves. Sweepback, angling the wings backward, effectively thinned the wing's profile relative to the airflow velocity component perpendicular to the leading edge, thereby delaying the onset of critical Mach numbers and mitigating the severe drag penalties. Shock waves are compression fronts where air pressure, temperature, and density change almost instantaneously. In supersonic flight, these waves originate from any leading edge or surface discontinuity. They carry significant energy, leading to a loss of thrust, structural heating, and an overall degradation of aerodynamic efficiency. Managing their formation and effects became central to supersonic aircraft design. To minimize the impact of shock waves, designers employed pointed noses and sharp leading edges. These geometries generate weaker, oblique shock waves that are swept back at an angle, rather than strong, perpendicular normal shock waves. Conical shock waves, emanating from sharp nose cones, further reduce drag by gradually compressing the air, distributing the pressure rise more efficiently across the airframe. Richard Whitcomb's area rule provided a profound insight in the 1950s. It stated that for minimum drag at transonic and supersonic speeds, the aircraft's cross-sectional area distribution, including the fuselage and wings, should be smooth and gradually changing. This led to the characteristic wasted fuselages, like on the F-102 Delta Dagger, allowing for more uniform airflow and reduced drag rise. The transonic regime, roughly from Mach 0.8 to Mach 1.2, proved the most challenging. Here, both subsonic and supersonic airflow coexist over different parts of the aircraft. Managing the complex interplay of shock waves, flow separation, and stability issues required sophisticated aerodynamic shaping, including careful camber and twist distribution along the wing, to ensure predictable control and efficiency during acceleration. At supersonic speeds, the mechanism of lift generation changes significantly. While subsonic lift relies on pressure differential created by airflow over curved surfaces, supersonic lift is largely generated by the pressure exerted by the air directly impacting the lower surface of the wing and the expansion of air over the upper surface behind a shock wave. This necessitated different wing profiles, often thinner and sharper. Supersonic flight also presented immense challenges for propulsion systems. Ram effect becomes significant, requiring complex air intakes to slow down supersonic airflow to subsonic speeds before it enters the compressor, preventing shock damage and improving efficiency. Afterburners, which inject and ignite fuel in the exhaust nozzle, provided the necessary burst of thrust to overcome transonic drag. The friction of air at supersonic speeds generates considerable heat, a phenomenon known as aerodynamic heating. This demanded new materials capable of maintaining structural integrity and strength at elevated temperatures. Aluminum alloys, common in subsonic aircraft, began to yield to titanium alloys and stainless steel in critical areas of early supersonic aircraft, and later to advanced composites. An unavoidable consequence of supersonic flight is the sonic boom, a loud, thunder-like sound caused by the pressure waves generated by the aircraft's passage compressing the air. While engineers cannot eliminate the boom, research has focused on shaping aircraft to distribute the pressure waves more diffusely, creating a low boom signature, or tailoring flight paths to mitigate its impact on populated areas. To achieve efficiency across the entire speed range, from takeoff to supersonic cruise, variable geometry wings, or swing wings, were developed. These wings could extend for low-speed flight, providing high lift and reducing drag, and then sweep back tightly for supersonic flight, minimizing frontal area and wave drag, a complex mechanical solution to a fundamental aerodynamic compromise. Contemporary engineering continues to refine supersonic flight. Computational fluid dynamics, or CFD, allows for precise simulation and optimization of airframe designs, predicting shock wave interactions and drag characteristics with unprecedented accuracy. Advancements in active flow control and adaptive structures also promise further reductions in drag and improvements in efficiency. The journey to supersonic flight was a testament to persistent engineering, driven by fundamental scientific understanding and clever design. From conquering the drag rise and managing destructive shock waves to developing heat-resistant materials and efficient propulsion, each step involved overcoming profound aerodynamic demons, culminating in the practical and efficient supersonic aircraft of today and tomorrow.